Okay, last we left off, we were talking about those hybridization bonds, right? Hybridization. You guys remember that?
Yep.
Okay, well, before we get started on that, kind of help me. There were two types of bonds that we had talked about as well, too. What were they?
Sigma and pi.
Sigma and pi. So
Oh, yeah, sigma is 1 and pi is 2.
what do you mean by sigma is 1 and pi is 2?
Oh, well, it's because yesterday I was learning them with Haley.
Okay. So, but what do you mean by
Yes, you told me we're gonna learn.
So what are we talking
Oh
about?
my goodness! I don't. Well, what we talked about yesterday, since she was helping me out with the one lab that I didn't know how to do. So she told me that there was, I don't know if he said if it was an atom that it was pi, and then pi means 2, and then there's a sigma that only means 1, so it's based on how many does it have. I don't really remember what she said, but I just clearly remember that sigma is 1 and then pi is 2.
Okay, but first we need to remember what it's making reference to. So what type of bonding are we making reference to? Are we talking about ionic bonding? Are we talking about covalent bonding? Are we talking about?
It's covalent bonding.
So it's covalent bonding. So we're making reference to covalent bonding. So when you make reference to that 1 and 2, what are you really making reference to?
Wouldn't be the bonding?
So it is the bonding, but what? Okay, so when we talk about bonding, what does that kind of imply? What's going on? And spatially, we're thinking about spatially. What's going on? You guys know what I mean by spatially, right?
Like how the electrons are being shared or transferred.
Yeah, like if one pulls the other one and then the other one pulls the other one, like that.
Well, no, that will be dealing with polarity, right? But yeah, but I mean, in terms of, you guys are like, you said if they're going to be sharing, or so yeah, we're talking about sharing, but really spatially, what do we mean by sharing spatially? What's happening to these orbitals?
Oh, they're overlapping.
They're overlapping, right? So in the case of a sigma bond, they're overlapping at a single point, right? And that's what you're trying to make reference to, Graciela, right? Gracia.
Yes.
Yeah.
Yes.
Okay.
It's just because yesterday I learned so much with Haley. So that's why. So I memorized a little bit.
Okay, that's good. That's good. Okay, so we're talking about that overlapping, right? So sigma is overlapping, and usually that's in terms of orientation, and who is it going to involve? So that sigma bond, which is one overlap, who can do that one type of overlap? And how's that overlap going to happen three-dimensionally? Let me put up a whiteboard. So you said there's one overlap, and then that means pi has 2 overlap. Is that what you're saying, Gracia?
Yes.
Okay, so who's going to be able to do that one overlap, and how's it going to be oriented so that it can do that one overlap? Anyone? Can the s orbitals form pi bonds?
The s orbitals can form sigma bonds and pi bonds, I believe so, yes.
The s orbitals? So the s orbital is just a
sigma bonds.
So it can form sigma bonds. So if I have two s orbitals, they're going to overlap to form a sigma bond. Okay. What else is going to form sigma bonds?
An s and p orbital.
An s and p. Okay. Can I form it this way, or can I form it? Which way is it going to form?
Side by side.
What was that?
The top one.
The top one? Okay. Okay, what about 2Ps? Was that? Is that a sigma bond?
No, that's a pi bond.
That's a pi bond. Okay. So how would, can 2Ps form a sigma bond?
They're both on their side. Or like
They're both on their
90
side.
90 degrees.
Okay. So an end to end. Okay. So if I have a double bond, what does that represent? So if I had C, one of these bonds are going to be what?
A sigma bond.
So one will be a sigma bond, and then one is going to be a pi bond. What about a triple bond?
One's going to be sigma, two is going to be pi.
Okay, so one is going to be sigma, and then the other two are going to be pi. Okay, you guys remember all that, right?
Yes.
Yeah, just brushing off those cobwebs. Okay, so now we're kind of familiar with that. We're feeling comfortable with that, right? And so we were talking about that, the sp hybridization. What does that mean again? Sp hybridization. You guys remember?
When they come together and form a new shape.
They come together and form a new shape. Why do they do that? What is the significance of it?
It makes it easier to bond.
It makes it easier to bond. So how does it make it easier to bond? Who said that?
An atom with an electron.
So you said it makes it easier to bond. And of course, we're talking about the electrons because electrons are what's going to be involved in bonding. That's correct. So how does it make it easier to bond?
Is it because it creates like two empty or two half-filled shells?
Okay, it creates two half-filled shells that are also going to be what? Got to be attractive. What makes it attractive?
Oh, yes.
So let's start there then. Can you guys see my screen?
Yes.
What do you guys see? Is it a whiteboard or is it? How about now? See it now?
Yes. Yeah.
Okay. So when we're talking about that hybridization, right? So for instance, we're talking about beryllium. Beryllium, we know, likes to do what? What does beryllium like to do? Well, first off, how many valence electrons does beryllium have?
2.
Where are those electrons located at?
In the S shell.
So, okay. 16s. Anyone?
1s.
Is it the 1s?
What was the question?
Question.
Where are those two electrons located? Was that the
Yeah.
question?
Where are the two electrons located?
The 2s?
It's going to be in the 2s, because we're talking about those valence electrons that are going to be available for bonding, right? So we're making reference to those valence electrons. We're looking at those valence electrons. Beryllium has 2 valence electrons, right? 2 electrons that it's capable of using for bonding. We also know that beryllium is kind of an odd metal, right? It prefers forming covalent bonds with 2 things. It's cool with having 4 electrons around it. It's happy with having 4 electrons. It's an odd case. It's unlike others, okay? So this is what beryllium looks like when it's all by itself. We see that both of those electrons are in the 2s subshell or orbital. Now, when it gets ready to bond, it takes one of these orbitals in the p and it combines it. So it takes an s and a p, and it combines those 2 to make what we call the sp orbital. Okay, so we have sp orbitals, and we're able to put 1 electron in each of those. Okay, these are higher in energy because this represents our energy diagram. The 2 p's are higher in energy, so it's going to be at that sp orbital, right? Now, think about it. If it was going to bond with something, right, and it wanted to have 4 electrons altogether, so if it was just using this guy, wouldn't that be a higher energy level than where the sp is located at? Because it's located about the energy level that it's at relative to the 2. Does that make sense? Let me do it differently. Say, if it was bonding with fluorine, right? Or chlorine in this case, chlorine is going to be donating 1 electron that it's going to share. So in this case, that electron would go up here in this situation, right? It wouldn't pair up with these guys, so it'd be inconvenient for that true interaction. But in this situation, it's able to actually pair up with it. And it's also at a lower energy level. So which is going to be more attractive, using this p orbital or using the sp, which is between the s and the p orbitals? Which is going to be more sexy? So the sp, right? It's going to be more sexy because it's lower in energy, right? So it's kind of like beryllium is showing a little bit of leg, saying, hey, give you a little bit of leg to chlorine to sit there and say, you want to bond with me because you're going to be lower in energy and I'll be in lower, right? So it makes it a little more attractive for bonding, okay? So the hybridization makes it a little more attractive or a little more accepting of bonding because it's lowering the energy level overall, right? So the overall energy level is being lowered, right? We're not utilizing these p orbitals. Instead, we're going to be utilizing a lower energy level called the sp. Make sense?
Yes, it makes sense.
Okay.
Yes.
So let's look at this compound. So we have BeCl2, right? So that's what's forming in this situation. So if we draw this, what does the Lewis dot structure of beryllium chloride look like? Who's going to be in the middle?
B.
Be
And then it will.
middle.
Yes.
Okay, and then? So I'm assuming Cl is going to be out here. And we know that
Yes.
Cl is going to end up having its 6 electrons around it. Okay, are they going to be any lone pairs on Be?
No.
No, because again, Be is happy with only having 4 electrons around it. Totally, it has 4 electrons around it. Okay, so what is the electron pair geometry for Be, that center atom? Electron pair geometry, the EPG.
It would be linear.
It would be linear. So how many attachments does it have?
Two.
Two. So it has two attachments overall, and it's going to be a linear structure. Since it has two attachments and it's a linear structure, then we know that it's going to take up two orbitals, s and a p. Okay, so we know that the hybridization is going to be sp. So let's say we have boron. Boron, let's say we have boron chloride. We know that boron is happy with having three attachments as well too, because we know that that's one of the exceptions that we've talked about, right? So what would that electron configuration look like?
B in the center and then Cl3 or three Cls around it.
Any lone pairs?
Not around B.
Okay, good. Okay, so what is the EPG for this guy? The electron pair geometry.
Trigonal planar?
Trigonal planar. How many attachments is that? Makes that trigonal planar.
3.
So 3 attachments. So in this case, this guy, if it does hybridization, it's going to have S, P, 2. That'll be a total of 3 orbitals, right? Because it takes 2 of the P's. How many orbitals are in the P orbital? What is the maximum number of orbitals in the P orbital?
There's 3 orbitals in each p.
There are 3 orbitals in the P, and we're using 2 of those 3, right? In this situation. Okay, so if we have CH4, what is the electron configuration? I mean, what is the Lewis dot structure for that guy?
Carbon's in the middle, and then it's connected by a single bond to hydrogen.
Okay, like this. So its EPG is going to be what?
Tetrahedron.
Okay, how many attachments?
Four.
So what would be its hybridization?
sp3.
sp3, that's correct. So I'm going to go to a whiteboard real quick. Okay, so if we have, let's see. So if we have this guy, what's going to be the electron configuration? I mean the Lewis dot structure.
With phosphorus in the middle.
Okay.
And 5 fluorine around it.
It's EPG.
Trigonal planar. Oh, trigonal bipyramidal.
That's right. So its EPG is trigonal bipyramidal. Okay, so trigonal bipyramidal. What would be its hybridization of that center atom?
Would you do like SPD?
That is correct. So it would be sp3 and 1d. That'll be a total of 5 orbitals. 1s, your 3p, so that's a fourth, and then the d, 1d, that'd be your fifth. Okay, so what about this guy?
Wait, so that means there's 5 sigmas, right?
That's right. It'll form 5 sigma bonds. That is correct. Because hybrids can only form sigmas. And this guy here. So what is the electron pair geometry?
Octahedral?
And its hybridization?
SP3D2.
Okay, piece of cake. Yes, no, maybe?
I have a question.
Yes.
So theoretically, what if you have like you have your center atom and you have a double bond? Would this double bond count as one attachment?
Yes, a double bond counts as one attachment because
Okay.
when we're talking about the hybridization, we know that the hybridization can only be sigma bonds, right? So hybridized orbitals will only make sigma bonds, right? That
Okay.
means that one of them will be the sigma bond and then the other one will be that pi bond. Okay, so your hybrid would be the sigma bond. So if there's a double bond, let me give you an example. That's a good question, Jessica. So
You're welcome.
let's see. There we go. Okay, so here's an example where we have 3 double bonds. All right, well, double bond here, and a double bond here, right? So this guy has how many attachments? What is his EPG?
Trigonal planar.
Trigonal planar. What is this guy's EPG?
The same.
And the last one, this carbon here, and then we'll talk about this carbon.
They're all the
Also the same.
trigonal planar.
They're all the same, right? They're all going to be EPG. So what is the hybridization? How many attachments do we have?
2.
Here? 3, because remember the lone pair is going to count as an attachment, right? So this guy has 3 attachments. This guy
3 attachments.
It also has 3 attachments. This carbon,
3 attachments also.
3 attachments, and then by default, we know that that one also has 3 attachments. So that's also part of the reason why it's trigonal planar, because it has 3 attachments. Okay, so this guy, so if we talked about the hybridization, it's going to be sp2, right? So this guy is going to be one of the SPs. I mean, sp2. This guy here is going to be in one of the sp2s. And then this bond right here is going to be an sp2 bond. Okay, now this one here is going to be a pi bond. Okay, and pi bonds are going to rely on having the p orbital. So you're going to have a p orbital overlap. And I'll show you this in the slides a little bit later. So this guy is going to be a pi. This guy, sigma, sigma, and sigma. Okay, so you're going to have sigma bonding occurring here, 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 and then this guy is going to be a pi bond occurring. Does that make sense? Because we know that with a double bond, one is going to be a pi, one bond is going to be a pi, the other one is going to be a sigma. And the sigma is going to be occupied by the hybridized orbitals. Does it make sense? Yes, no, maybe?
Maybe.
Okay, so let's see. We'll see if it does after we get through everything else. Okay, so here, this is the case that we were talking about CH4, right? So if we draw our energy diagram, we know that how many valence electrons do we have in carbon?
4.
We have 4 valence electrons. So it looks something like this. This is 2p, 2p, 2p. Okay, so the hybridization, where's that going to be located at? And then what is it going to be called?
SP3.
So it's going to be sp3, and it's going to be located somewhere between the 2p and the 2s. So the hydrogen would come in and be sharing its electron in that orbital, right? It'll take its s orbital and share it. So literally, hydrogen, this is hydrogen. This represents that carbon. So this would be the s orbital of hydrogen overlapping with that. Okay. You guys see that?
Yeah.
Okay. So if we were talking about ethane, right? So ethane would be chemical formula. Let's see. Okay, so it has 4 sp3 orbitals, 1, 2, 3, 4. And then the hydrogens, this is the s orbital of the hydrogen, of each hydrogen. This is the s orbital of each hydrogen. So these guys would come together, end over end to end. And then the s orbitals of the hydrogen would be out here. Make sense?
Yes, it does make sense.
Now, if it doesn't make sense, you need to say something so that I don't just leave you back in the woods. Okay. So here's an example of SPD, right? 1, 2, 3, 4, 5 attachments. This guy, 1, 2, 3, 4, 5 attachments. This guy, 1, 2, 3, 4, 5 attachments. So this is a case of all of these guys are going to be sp3. This guy, 1, 2, 3, 4, 5 attachments, right? Again, sp, spd for each of those orbitals. So, oops, here we have 6 attachments. 1, 2, 3, 4, 5, 6. SPD2. Simple? Yeah, no, maybe? Okay, good. So let's take a test. You ready?
Yeah.
Okay. Let me pull up a whiteboard or a quickie, quick quiz. Let's see, hold on. Sorry, I'm having a little trouble pulling up what I'm looking for. Ah, there we go. Okay. see. Oops. Oops, wrong poll. Hold on. So let's go add. Ah, shit, cancel. Okay, there you go. Can you guys see the poll? Can you guys see the poll? Can you guys hear me?
Yeah, I can see
Yeah.
it.
Okay. So you guys know how to do polls, right? You got to vote. Okay, 3 more people. Are you guys there? Oops, if I can spell hybridization. 1 more person. Is that Jessica? Did you not vote, Jessica?
No, do you want me to vote?
Yeah, vote. Put your vote in.
Okay, I'll just submit what I've done. There, sorry. That's not the answer though.
Okay. Everybody got their vote in? Crap. Oh, that's pretty good. Okay, so let's start with the first one. BEF2. Oops. BEF2. So what is the Lewis dot structure for the BEF2?
BE in the center and then F2 And then there's a lone pair around BE.
Is there a lone pair around BE? Everybody want to make a bet?
No.
No,
Now,
there's no.
so remember, BE only likes to have 4 around it. 4, excuse me. So it's happy. It's happy that way. So what is the EPG?
Linear.
Linear. Linear is when you have how many attachments?
Two.
2 attachments. So we have 2 attachments. So we're going to need to use 2 orbitals, right? 1 for each electron. So we're going to need an S and a P. That's 1 orbital, that's 2 orbitals. So the correct answer is SP. How many of you guys put that?
Me.
Okay. So in the case of the XC F4 electron configuration looks like this. So how many attachments is this? Anyone?
6.
6 attachments. So if there's 6 attachments, then what is going to be the EPG?
Octahedral.
Octahedral. Okay. Okay. So 6 attachments. So we needed 6 orbitals. So we have the S, we have 3 P's, and there should be 2 D's. So the correct answer isn't even listed, right? Kind of really threw you off. Okay, do you guys understand why because for each electron, there needs to be an orbital accounted for, right? So this guy needs to have S, 3 P's, and a D to kind of account for all of the attachments that are going to be needed. Does that make sense? Yes, no, maybe?
Yeah.
Yes.
Yeah.
I have a question, Dr. Henry.
So
Can you
somebody
hear
was,
me?
I can't hear you. Say it again.
Can you hear me now?
I can hear you now.
So before we actually move on, when it comes to the Lewis dot structures, what are the exceptions? Because I know like xenon, beryllium is an exception, right?
Yeah.
Are there any other elements like them?
Let's see. No, so beryllium, we know likes to have 4 around it. We know boron likes to have 6 around it, right? And we know xenon can be pushed. So anything that's below xenon that is a noble gas can actually be pushed can be pushed, particularly by fluorine, into a reaction, right? So then
Okay.
any noble gas below that. So radon, or sorry, radon is Rn. Okay, so xenon and radon, both of those could be pushed into forming hybrids and utilizing that d orbital, right? We also know that all the ones that are in the third energy level, well, those guys can actually utilize the, let me go back to the periodic table. Give me 1 second. Clear. Okay, so we know that all of these guys here that are in the third energy level, right? And anything below here, these guys can also be exceptions as well, because they can be hypervalent, right? So since all of these guys can be hypervalent, in other words, they're able to use the d orbital, right? These guys are able to use the 3D because it's in that energy level and it's accessible to those electrons. And so they can be pushed up in that energy level, or they can be used to form hybrids. And that's essentially what's happening in this case. Okay, does that make sense?
Okay.
Okay, so
Yeah.
in a sense, you have a lot of exceptions, right? So now you just got to expand your thought process, because anything that is able to utilize that next energy level, that D subshell, is going to use it if it needs to. It's a possibility. So does that help?
Thank you.
Okay. No problem. Okay, so draw the Lewis dot structure, right? And then you can kind of use the Vesper theory, right? Or use the electron pair geometry to sit there and determine the attachments. So if there's 4 attachments, then it's going to form what type of shape, and then what is going to be the hybridization. Four attachments. What is going to be the shape? Tetrahedral. So tetrahedral. And then what's going to be the hybridization of the center atom? Somebody said it. sp3. That is correct. Okay, if it has 5 attachments, what's going to be the hybridization?
SP3D.
sp3d. 5 attachments, sp3d. If it had 7 attachments,
E3D2.
you said sp3d what?
2.
Would it be 2? Because if 5 is spd, then 7 would
3D.
be 3. Yeah. So 6 attachments, that would be sp3d2. Okay, does that make sense? And so why can't I say sp4?
There isn't 4 orbitals
Okay,
in the P.
okay, that's right. This will never happen because there's not 4 orbitals in a p subshell.
For like the ones, I'm trying to think of like, I think it's Mercury.
Mhm.
Where would it P like 1 and then D something? A P orbital to a D.
Mercury? So you're just saying for the electron configuration?
Yeah, I'm not sure if it was mercury.
No, you're not. I know what you're talking about. Let's say silver or gold, right? Right here. So like for instance, silver, if you take a look at this guy, it's gonna have its core. Ag core krypton. It'd be 5s1 4010. So you're going to ask me right here is an example where it, instead of having 5s2 49, because it's 1 2 3 4 5 6 7 8 9, that's shown in the d orbital, it actually will take 1 here and fill this guy up because it's more stable to do that. It's less energy overall for silver to do that, right? It's also the same thing that happens here in the case of copper. Okay, so is that what you're asking me?
Yeah.
If you're able to sit there and fill up the D shell, you want to do that if you can, right? If you're, well, let's just say, if you're close enough to do that, right? So if you take a look at this guy here, it does exactly the same thing. That's why you have that 1 there. So that would be the 6th orbital. So you'd have, in this case, for gold, it's really Au xenon 6s1 or F14 5d10. Okay, because it's actually going to get that extra electron to fill this guy up. Now these guys here, take a look. If you click on them, okay, so this guy, nickel is 2 away from filling this up, but nickel is kind of a weird one. He likes it, he would prefer, it's lower in energy, for it not to fill up this entire shell. So it's not going to borrow both of the electrons from here at all. It's just going to go ahead and fill these guys up first, and then go ahead and fill these guys up. Where palladium will actually take the 2 here and then put them in the 4d orbital. And you can tell that by there's no 2 located in the 5s, right? So that's 1 2 3 4. This is the first energy level. This is the second energy level. This is the third energy level. This is the fourth energy level. So if you count the numbers, it has 2 in the S, it has 6 in the P, and then it has 10 in the D, and then it also has 10 in the 10 in the D. Sorry, 10 in the D. That's it for the 4s. And so that's why it counts up to 18. Does that make sense?
Yeah.
Okay. So if you're the 4th one, like chromium, it's better for this to be half full, so then everything has polarity. So we know that the D has 5 orbitals, right? 1 2 3 4 5. So this represents the D. So we know that we have the 4s in this case. So we'll say this is going to be the S. So it has, instead of, we would expect it to do this in the case of manganese. This is what is expected, but it's more stable for it to have another electron up here because it makes balance, right? It makes, if you have one in each orbital, it kind of balances it out. And so it makes it a little more stable. So it'll actually borrow one of those electrons and put it up here. So it would have a half full shell, right? And it's more stable to be half full or completely full than to have one here and then just be almost half full. You know what I'm saying?
Yeah.
Okay. So if you look at this, that tells you that there's going to be one in that s orbital that's at that higher energy level. So that's 4s 3d, right? So 4, 3. So then that lets us know that that's in the 4s. So if we go down here, right, it tells us what it's going to do. It tells us what it's doing, you know, in this case. So where manganese, oops, that's the wrong one, chromium will actually borrow from that one. And then mobidium would also do the same thing. It has that one that's left, right? Tungsten doesn't. Okay, it doesn't borrow from this guy. Okay, does that make sense? Are you with me?
Yeah.
Okay. And so you can use the P table to sit there and help you do it. If you guys noticed on your periodic table that's actually printed out, if you look close enough, you can actually see those same numbers on your periodic table. Okay, I don't know if you guys can see it or not. Okay, so how are we doing on time? Okay, so you guys remember when we talked about groups and groups having similarities, right? Did I say that they were exactly the same? Like in terms of reaction. So like sulfur is going to behave like oxygen, right? It's also going to behave like oxygen.
Sulfur.
Okay, sulfur and anyone else? Alberto, who else behaves like oxygen?
I'm sorry, what was that?
Who else behaves like oxygen other than sulfur?
Sulfur.
Other than sulfur?
Selenium.
Selenium. Okay. So things that are in the same group behave like each other, right?
Yep.
Are they exactly like each other?
No.
So we're not going to expect them to behave exactly like each other. They're just going to have these, they're going to have some similarities, right?
Yeah.
Okay. So here I have 3 molecules. I have water, I have dihydrogen sulfide, and I have dihydrogen chloride. So they behave exactly like each other. They have the same electron configuration, they have the same electron geometry, but the difference is that their angle is going to be different, right? So the reason why their angle is going to be different is because as you get further and further away from the nucleus, you're going to have other factors that are going to affect this, right? So this guy is kind of closer to the nucleus. So we know that the electron pair are going to try to push themselves pretty far away from each other, these electron pairs, right? Well, these electron pairs are going to do the same thing, but they're going to be pushing this guy even further away from each other. And then these electron pairs, because they're further out, they're going to do it even more, okay? And so the angle between the 2 hydrogens, so this is a hydrogen, here's the other hydrogen, is going to get smaller as our molecule is going to get bigger. So if we're talking about selenium or dihydrogen selenide, what would we expect the angle to be, roughly?
$91
It'll probably be one degree between it, so like 91 roughly, right? So somewhere in between the two, based upon the general trend, right? And so does it make sense that the further away that you get from the nucleus, those lone pairs are going to try to push themselves even further away, because they're going to be the outer shell, and they're going to try to push those attachments, because those attachments are going to be relatively close overall in terms of that interacting compared to those lone pairs. Yeah, no, maybe? Yeah, no?
Yeah, I kind of understand. Yeah.
Okay. So if we had, say we had this guy.
Wrong, but yes.
This guy, even though this won't happen, but if palladium was to form a covalent bond, right? But we know that it's a metal, it actually doesn't. But if it did, we would assume that its angle would be less than that. There's a point where it can't go any further, right? Between these two. And so that 90-degree point is what's going to be the limit. Does that make sense?
Yeah. No, yeah.
So it'll be at 90 degrees, and then these guys would be as far away as they could possibly be. And that's it. Okay. Okay, so let's see how much you guys learned. Okay. Gracia, start with you. So what is the hybridization of the sulfur atom and the sulfate ion? So the electron configuration looks like what? I mean, the Lewis dot structure, not the electron configuration. Lewis dot structure looks like what? Anyone? Gracie, are you there? Okay, Mikey.
Sulfur's in the middle.
Sulfur's in the middle. Okay. And so that means we have oxygen. Are they all single bonds, or are there any double bonds? Anyone? Okay, so we need to put this on test. Single bonds?
Did you ask if there are double bonds?
Are there any double bonds? Yeah, I'm just putting stuff here since you guys are not getting responses.
I don't think so. I think it's it would all just be single bonds, and then oxygen has like all the valence around it.
So like this. So what would help me figure this out?
There has to be.
What was that? I can't hear
There
you.
has to be double bonds.
There has to be double bonds.
Formal charge will help, right?
That's right.
So there are two double bonds, if I drew my structure correct.
Okay, so negatively charged, correct? Okay, so how many attachments do we have?
4.
We have 4 attachments. So then it's going to be,
Tetrahedral.
it's going to be tetrahedral. And then what is going to be the hybridization that's formed?
SP3.
sp3. Okay, that is correct. What about selenium tetrafluoride?
Selenium in the middle. Fluorine around it.
Okay. Any lone pair?
Others.
Somebody started saying something? Do we have a lone pair? Yes, no, maybe?
Yes.
Yes.
Okay, so we got a lone pair. Okay, so what is the hybridization?
Trigonal bipyramid.
Okay, so the EPG is trigonal bipyramidal. And the hybridization?
SP3.
SP3. Anything else?
D.
D, okay. Okay, what about urea?
Nitrogen. Nitrogen would be connected to carbon.
Okay,
Carbon connected to oxygen.
Why is the O in parentheses for the formula?
it's to let us know that it's connected to the carbon. So it says, it's letting us know that that carbon, that oxygen is attached to the carbon, and as well as the nitrogen here and that nitrogen there,
Okay.
to try to help you with the Lewis structure. Okay, so this nitrogen, what is the EPG?
Tetrahedral.
Okay. Okay, what about the carbon?
Trigonal.
Trigonal what?
Planar.
And then of course this nitrogen is going to be the same as this one. So it should be tetrahedral, right? Okay. The hybridization.
SP3.
SP3. Okay, what about this guy?
SP2.
SP2. And then we know that this guy will be the same as the first one, SP3. Piece of cake?
Yay.
Good, good. Okay, here we have acetic acid. What is that going to look like?
Carbon connected to carbon, and then there's 3 H's around one of the C's.
Okay.
There's oxygen.
And then yeah, an oxygen, a hydroxide.
Okay, so this carbon, what is the tetrahedral? That kind of sounded a little scary. And the hybridization?
sp3.
Okay. This carbon?
It's a trigonal planar, and the hybridization is sp2.
And this guy?
Tetrahedral. And it would also be sp3.
sp3. Okay. Okay, so remember when we were talking about those pi bonds, right? So here's a case where we're actually going to have a pi bond, right? So first we're going to have, take a look at our image here. So we have the hydrogen and this hydrogen interacting with the sp2, sorry, orbital. So that one sp2 is interacting with this hydrogen. So sp2 is interacting with this hydrogen. And then you also have one of the bonds being a sigma bond. So you're going to have this sp2 interacting with this guy's sp2, right? And we know that hybrids can only interact with sigma bonds, by sigma bonds, okay? So the double bond is going to be here. The dotted line represents the double bond for me. So you're going to get this overlap to form your double bond. That second bond for the double bond. Okay, and that's going to be your pi bond when you have these guys overlapping this way. Okay, does that make sense?
Yes.
Yeah.
Okay, so in the case of a triple bond, so this guy is, it's C triple bond H. We know that in this case, how many pi bonds are we going to have?
2.
We're going to have 2 pi bonds, right? So you see the 2 pi bonds that are actually forming. Here's your first pi bond. Here's your second pi bond. And then you have hydrogen interacting with one of the sigma bond or one of the sp bonds to form a sigma bond. And you have overlap between the 2 SPs to form the other sigma bond. And then that would just be that other carbon, the SP of the other carbon, forming a hydrogen bond. I mean, forming a sigma bond with the hydrogen. Okay, simple?
Yeah.
Okay. Okay, so when we talk about hybridization, right? Hybridization is only going to evolve the bonds, you know, and in a lone pair. So it's not going to affect, hybridization is not going to affect resonance structures. So in this case, we have a resonance structure of benzene. So this double bond is shifting from this one to this one, to this one to this one. Okay. So, but since it's shifting, it's not going to affect, hybridization is not going to be affected, or I should say, resonance structure is not going to affect the hybridization assignment. Okay. So that resonance does not influence hybridization at all. Okay. Now, knowing that, if we have sulfur dioxide, this is the structure for sulfur dioxide. So what would be the hybridization of sulfur dioxide?
sp2.
Okay, and it's not going to be affected at all by that resonance structure. It's going to end up being the same. So does that make sense?
Yeah.
Yeah.
Okay. So let's see. I remember where I stopped at. Yeah, we're gonna go ahead and stop here. We'll pick this one up when we get on Wednesday. Okay. Are there any questions? How many of you guys still have to take the exam?
Yes.
Me.
2 of you guys only? That's pretty good. Everybody else has already taken it.
Dr. Henning, I kind of had a question regarding the next lab.
Yep.
I don't know if this is like getting ahead, but I remember doing that lab with Mr. Bella.
Yep.
And it was involving like hydrogen bonds and like ion dipole and all that stuff. Are we supposed to go over that before we finish the lab?
Yeah, actually, I'm gonna extend your lab when that lab is due, since we haven't gone over that material. So the idea is
Okay.
that I would technically have gone over it today or tomorrow or on Wednesday. Yeah, if we don't
Okay,
get
yeah.
it done, then you don't have to worry about that.
Okay, I just wanted to make sure that I wasn't like misremembering or anything.
Nope.
All right.
Okay. Any other questions? Okay. Let's see. Is there there's no other questions? Okay.
Nope.
So then I will see you guys on Wednesday. Finish up the exam. Good luck.